Welcome back, physicists. Weird. Total brain hiccup. Sweet. We're looking at trig. Real quickly, you guys can see it was on the board. So katoa, so is what, Fern? The sine of an angle theta, how do you evaluate it? It's just a fraction. Opposite over hypotenuse. Cool. Kalisha, ka from so katoa. What's ka represent? The cosine of a function or of an angle theta. And how do you evaluate a cosine, or how would you determine a cosine? Adjacent over hypotenuse, CAH. And the last one, Toli? Tangent is TOA, and how do you evaluate a tangent of an angle theta? Perfect. Now, looking at this thing, the unit circle, again, you are not going to have to memorize it. The unit circle is special. Anytime you see unit show up, a unit square, a unit circle, doesn't matter, a sphere. What makes it unit? There's something special about this circle. So, say it again. The degrees. So, I wouldn't say that's special and unique about this circle, but you're absolutely right. How many degrees are on this circle? 360 of them. Cool. Beyond that, how many radians? Just a quick check. There's 2 pi radians along this. Now, if I said, hey, imagine any circle, and I want you to be able to tell me to draw it, you really only have to give me 2 pieces of information if it's on the coordinate plane, or 1 piece of information if it's not. If I said, draw a circle, how do I specify to you how big of a circle I want you to draw? What value would I give you? Say it again. Would I tell you the circumference and you guys would measure a piece of string to get the circumference and then you'd line it up and make it a nice circle? Louder. It's the radius. Now, the unit circle is a special circle. One of the special things about it is a radius that we elect to use. What is the radius of this unit circle? So you're giving me degrees. If we're looking at a radius, you should be giving me a distance. From the center to the outside, no matter where, on this circle, what makes it a unit is that its radius is 1. Now, I don't know how hardcore you guys hit it in Algebra 2. You use these books, right? Did you guys have to memorize the unit circle last year? Anybody remember any parts of it? Okay, so when you're talking about pi stuff, you're looking at the radians for the angles. Just a fun fact, 2 pi comes from the fact that if you were to find the circumference of a circle all the way around it, this radians, I know they feel unnatural, they're the ones that we should use. Degrees are made up. They're completely arbitrary. I could have picked 100 degrees, which in hindsight, maybe we should have because that's what metric stuff would do. I can imagine 100 degrees makes a full circle, which means right angles would be 25 degrees, and all of math would change the way we write it, but the concepts would all work the same. So a couple things just real quick for fun facts. Why 360? Why on earth did they arbitrarily pick 360 degrees? Because it was a choice. Any ideas? Okay, when you learn to count, I assume you use these bad boys, right, initially? Which means you count base 10. We count to 10 and then we start restarting, right? Now, you can count in any base that you want. And you just start adding the next numbers, and it's weird to think about, but like base 4, 1, 2, 3, 10, 1, 13, or 11, 12, 13, and you just start adding the next digit in front of it. It gets weird. 360 is close to some things that really exist, though. Kind of close to something that's important that even 5,000 years ago, Mesopotamians knew about it. What takes approximately 360 times? Days. Is a year, right? 365, so that's close. Pretty natural to think that. Really not the case. I want you guys, can everybody in here count to 12? Right? I'm pretty sure of it. Okay, can you count to 12 on your hand? Not hands. Can you count to 12 on your hand? Love it. Have we done this before? Yeah. Weird. Was it in this class? I don't remember either. I don't know where it would have shown up. We talked about circles in pre-calc. Check it out. If you look at your hand and you make a little claw, you guys see creases on your knuckles? Okay, now we have these fancy things that are known as opposable thumbs. Check it out. I'm going to point to each crease. 1, 2, 3. There's 3 creases as I count up. 1, 2, 3, right? So check it out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I'm now at 12, and I can count to it on one hand. This is it's not natural for us to count this way, but it's how it used to be. If I want to get to 13, check it out. Here's 12. Here's my placeholder. 13, 14, 15, 16, 17, 18, 19, 20, 24. 24. We can count all the way up to 60. Now, it turns out that 60 is super duper nice. Base 60, there's a lot of things that go into the number 60, right? 1, 2, 3, 4, 5, 6, 10, and then there's several more. 360 is a really easy number to get to because all of it's 60, and 60 has a ton of factors. Convenient to use, but that's it. Now, looking at this, we're going to discuss the unit circle really briefly, and just to check, anywhere on this circle, we have an ordered pair, right? Now, normally ordered pairs take the form x comma y. Everybody cool with that? So, check this out, though. Instead of x and y, we can represent these by the angles that get formed. So, check it out. The x's are our cosine of some angle theta, and the y values are the what? I think, did I hear it? It's just, okay, I just couldn't tell for sure. Sine theta. Now, for this, when you first see this, and you see a little bit of it in algebra 2, you see a little bit of it in pre-calc, or sorry, geometry, we're going to make use of a couple old ideas from geometry that you may not remember. We all know that right triangles are super nice because you get Pythagorean theorem to work out, yeah? Okay, here's what I want us to envision, and if you want to do this on a scratch paper, you can, but it's all going to fit in here. There's a couple triangle shortcuts that you guys learned years ago that you probably don't remember. So these notes are going to be just chaotic because I'm just catching you up like as fast as I can to use this stuff. Okay, so right off the bat, within our unit circle, we'll come back and we'll visit it. I'm going to go actually below it or next to it, and I'm going to do it up here in my notes. We're going to use a couple special triangles, and we're going to see that the unit circle is really easy to build. Now, special triangles, not that, you know, that the ones that aren't included here aren't special, but there's two that we use all the time. Do you guys remember any special right triangles that you've ever seen? Two flavors of them. That's 30, 60, 90. So let's dig into that one first. A 30 degree, 60 degree, and I'm not going to use the dash because it looks like a minus. A 30, 60, 90 triangle. Now, if I asked you guys to roughly sketch a 30, 60, 90, could you? Probably. This part, you do not have to draw the whole one, but I promise that we're going to get a 30, 60, 90 out of it. I'm going to temporarily draw as best I can, an equilateral triangle. Roughly equilateral there. Close, right? Okay. If we have an equilateral triangle, I'm just going to pick an arbitrary length. What do you want the length of any side to be? They're all the same. Say it again. Oh, I didn't know where it came from. 30 for the side length? We can do that. Can I pick a slightly easier number just because, and we'll see why? Oh, we'll get to the angles in a second. I'm going to say this is length of 2. And I'm doing this intentionally, and we're going to generalize it here in a second. If this side has length of 2, what's its length? 2, and the bottom length would be, so check it out. What are each of these angles? If it's equilateral, they all have to be the same. 60 degrees each. Now, I'm only going to label this one for now. Okay. There's one special segment that I could add to this triangle that you guys have done. And anybody remember the shortcut just before I go into like super detail here? Okay, check it out. I'm going to drop an altitude from this point. Here it is. We're not going to prove any of these ideas, but check it out. If it's an altitude, it's vertical, right? What angle just got formed down here? 90, which in turn means this angle up top was just bisected. We get a 30. Our 30, 60, 90 triangle comes directly from this equilateral. Everybody on board with this right now? Okay, we're going to take one little step forward and we're going to see our shortcut. Gosh, if this whole length was 2, what's this length? 1. And then do me a favor real quick. I want you to find me the height. It'll take a minute, but you now have a what sort of triangle just on this side? Oh man, how many sides do you know? Could you find the third? Do it. Right meow. Cool. Pythagorean it up. Pythag it up. I don't know how to word it. Cool. So in this, you know what this is actually. It is. If I had changed the base to x, would you know how to do it? So, like, you should draw me at 30, 60, 90, not to draw the whole equilateral. And then do me a favor, label this at x, and just make sure 30 and 60. If this is x instead of a number. We get root 3. Like, it's ugly, right? Let's check just to verify. What do you want me to call this for now? It's unknown. I'm not going to let you pick. I'm going to call it h because it's the height of this triangle. Cool. If we try the Pythagorean theorem, let's see. We know that h squared plus 2 squared, just kidding, plus 1 squared is equal to what? Okay, h squared plus 1 is equal to 4. H squared equals 3, and h is root 3, right? Okay. Now, I don't really care about that work right there. And I actually don't even care about that half of the circle anymore either. We just determined that this is root 3. Does this look familiar to you, or does this seem like, so what, Holloway? Who cares? It can be the second one. That's okay. It doesn't hurt my feelings. You guys don't remember seeing this directly. It's been a couple years. My guess is you saw it last year in algebra, and I checked with Osman. I think you guys did trig towards the end of the year last year. So it should be kind of fresh, but if this doesn't ring a bell, this is going to make stuff so much easier, and maybe it's why you didn't love trig. Now, there's a relationship. I'm going to make you guys repeat after me with, you can change one word. I don't care if it's king or queen. Doesn't matter. Okay. The short leg of this triangle is the queen. It is the most important part. The short leg is the most important part of this entire triangle. The short leg is opposite from which angle? The 30. The smallest side is opposite the smallest angle. That's an old geometry idea. I'm going to label one more little thing. Short, long, and a height. Now, we'll come back and add in that opposite adjacent lingo and stuff here in a minute, but let's look at it. The short leg is queen. What's the most important side of this triangle? 100%. Hypothetically, and we can check it out with different numbers, but is there a relationship or something that we could do to get from a length of 1 to the hypotenuse as a length of 2? We just double it, right? So I'm just going to pick another one real quick. Let's say we had, and you don't need to draw this one. I just want to verify this works. Let's say that this was 8, which means this would have been 4, right? If we do the same thing. And this is h again. Let's check it out. Hey, it's always going to work this way automatically, right? So here we go. 2 little shortcuts and the special triangles that we use, and then we'll go back to the unit circle. We're going to do another triangle here in a second. Short, which leg is queen? Short leg, queen. Short leg equals queen. You can say king if you'd rather. Oligarch, whatever, I don't care. Monarch, it doesn't matter to me. Okay, to go from short leg to the hypotenuse. What do? We just take the length here and multiply it by what? Short leg times 2. Cool. Bless you. Now, this one's going to feel less natural, but how about to go from short leg to here? And I'll pull up that other one that we had that was 8 and 4. Could we Pythagorean theorem this one out? Like, you guys could, right? Okay, so check it out. H squared plus 16 equals 64. Help me solve this. H squared equals... Good, 48. And now what am I going to do? I'm going to take square root. Now do me a favor, break down 48 such that there's a perfect square in it. H equals the square root. I need 2 numbers that multiply to be 48, hopefully with a square. 4 times 12 works, but there's a bigger one. So 6 times 8 works, but neither of those are squares. Ooh, I like that number. 16 times 3. Do either of these numbers have a square root? and it'd be a 4, right? So this one becomes 4 root 3. This one became 1 root 3. To go from the short to the long leg then, what does it seem like we're just multiplying by? Short leg times root 3. Short leg times, oh my gosh, it's the square root of 3. Again, short leg times root 3. Now, we have used a concrete example for this. You can change it if you want to the generalized form. Instead of saying that this is 1 and 2, like those numbers are nice to think about, but generally, at least when I taught it, and I don't know exactly how you guys learned it last year, if I just want to say, hey, this works for any known length, I don't want to have to write infinitely many of them. I'm going to call this leg x. What's the hypotenuse? 2x. I'm just doing short leg times 2, right? How do you get to the long leg? Cool, so it's x times what? Root 3, Riley whispers confidently. Okay, this shortcut is going to show up over and over and over and over on your unit circle. One more type of circle to deal with. What's the other sort of circle? Sorry, that's a wonky comment to make. There's only one sort of circle that's circular. What's the other special triangle? 30-60-90s are pretty, they're sweats. I don't know if that works or not. Oh my, 45-45-90. Do me the same thing. You guys are going to do just a Scotia math here. We have 30-60-90s that are awesome, and we have our 45-45-90s. I want you guys to knock out the 45-45-90 shortcuts for me, and I'll share with you a little thing that I use to remember them. But I'm going to pick this. If this is x, what is this? It's x because it's an isosceles. I want you guys to find me from general form like this. Gosh, if this x is the length, find me the length of the hypotenuse. I'll give you a second. And this one, because there's no short leg, once you guys get it, I'm just going to say leg to hypotenuse. And there's always something that's going to happen. We're doing it in the general case already. Pythagorean theorem with what we have, you can call this h or whatever you want. But let's find that shortcut real quick. You need to take either leg because they're the same length, and I multiply it by what?
2.
Not just 2. Kalisha, what did you say we multiply it by? Root 2, or the square root of 2. Check it out. We can write these rules if you want. Typically, when we do these, I only ever do this. This tells me my rules. Now, my stupid way that I remember it, and maybe it's not stupid because it's worked for me for the last however many 100 years. Hey, thanks for at least slightly exhaling out of your nose. 30, 60, 90s. How many different side lengths, or how many different angles do they have? Root 3 shows up on a 30, 60, 90 with 3 different angles. How many different angles will you find on 45, 45, 90? And what do we multiply by? Just so we don't multiply the x time like we do, and I just want to fix your language. Just root 2. 3 different angles, use root 3. 2 different angles, use root 2. Now, I'm sure that over and over throughout the day I sound like a crazy person, and that's okay. I'm going to sound like a crazy person for a minute. We're going to go back to the unit circle. Okay. When I think trig, the very, very first thing that comes to my mind is bow ties and butterflies. Like, legitimately, I think this every single time, and it seems kind of silly. When we look at it, what did you guys, what's the radius of this circle? It's a radius of 1. Don't draw this yet, but I just want to think about it. Could I draw a 30-degree angle out to here? And again, don't sketch this on here yet. I could put 30 degrees here, right? From this point, could I drop straight down? Which means this is a what angle here? What sort of triangle do I have? It's a 30, 60, 90, yeah? Everybody cool with that? Check it out. What's the hypotenuse? It's 1, because it's the radius of our circle. Everybody still on board? Okay, am I going way too slow with this? Okay, should we do some up downs or something? I don't really want to do up downs, but if it'll help you guys. Real quickly, you guys have seen my super frown, I assume. I want to see your biggest possible frown. As frowny as you can get. Show me how frowny. Not sour. Oh, that's a frown. Okay. No, that's a scowl. That's a scowl.
Yes, it is.
Show me.
I can't do it anymore. I can't do that.
Okay. We're gonna make a deal. If I try to read facial expressions, I assume all your teachers do, right? It's early in the morning, I get it. If I'm not gonna get anything like super meaningful out of your facial expressions, that'll happen, I understand. At least make silly faces so I have something to entertain me to take away from the awkwardness. Super frowns preferably, but whatever you want is fine with me. Cool. All right, check it out. Help me out here. If this is length of 1, do you agree that this ordered pair is on the circle, like it's there? And it's this distance over in the x direction, and it's this distance up in the y direction. Everybody on board with that? Okay. Which side of this triangle's queen? The hypotenuse, the vertical, or the horizontal? Vertical, because that's opposite the 30, right? If this had been 30 degrees, this is my short side, and we know the hypotenuse. To go from short to hype, what do you multiply by? By 2. What if you just change the direction? What about from hype to short side then? Instead of multiplying by 2, what should we do? Divide. Now, you have just identified for me that this distance up was 1/2. Hey, look at that. That's our y value. What's this other side? Now that I know that this is 1/2, what do I multiply it by to get to the long leg? With 3 different angles. Square root of 3? Love it. What's 1/2 times root 3? Can I just write it like this? Okay. All of a sudden, if you remember it well, which you may or may not, Algebra 2, you don't have a ton of focus on trig. This is what I tell students when I teach pre-calc, that this is all you need to remember the unit circle. Do you guys agree with that? Maybe. Okay. Now, I'm not going to go through it. Again, this isn't a math class because we're not going to get every single piece. The way that I always teach the unit circle, I think it's the easiest way to possibly do it. 30 degrees is a special angle. What was another special angle that came out of those triangles? 45. So quick little check. Anybody remember the value here? The next point on the unit circle. Say it again. Root 2 over 2. Now check, just again, we're not going to do the whole unit circle. I just want to discuss it because we're going to see a bunch of these angles. Can you guys count down from 3? And can you count up from 1? Check it out. 3, 2, 1. We're going to skip it. And then let's start counting up. 1, 2, 3. And all of a sudden we just get this cycling repeating through, and you have the entire unit circle that you can construct here. Okay. You do not need the entire unit circle in here, but it will help. Okay. I'm going to go back to my crazy comment. Bow ties and butterflies, because there's always an issue when people deal with the unit circle. Every quadrant could have a triangle in it. I could draw a triangle here. I could draw another triangle up here in quadrant 2, and there's a bunch of them, right? When I talk bow ties and butterflies, here's my thought. If I go here and straight down, what does this look like to you? If I go all the way through all 4 quadrants of my circle. It's a bow tie, or if you're a little creative and we do this, now it's a butterfly. Bow ties and butterflies tell us how we should draw these triangles. Now, this is going to happen at every single angle. Here's my roughly 30. Here's the 45 bow tie and butterfly, and we'll just see it happens again. No matter where you are on this unit circle, you're going to get these triangles that show up that are either 30, 60, 90s for our nice angles, or they're going to be wonky. We have to use trig for it. Every bow tie, every butterfly just showed up there. It looks really complex when you have all of them up, but notice if we just focus on any one triangle, piece of cake. There is a triangle that I guarantee 60 degrees down here, 30 degrees up here. It's a 30, 60, 90. All the same rules apply. You never have to memorize the entire unit circle as long as you know bow ties and butterflies exist. Cool. Good on that one. All right. We're just going to stick with the trig part for a second, and then we're going to apply it in a couple different situations. Trig, SOHCAHTOA specifically, works really well if you have what sort of triangle? A right triangle. Okay. Now, it works really, really nicely for our purposes in the way it's just presented. 30s, 60s, and 45-degree angles are always super convenient for us. Are there angles out there that aren't those? Which means you need a way to deal with other situations, right? So, 2 ways to go through this, and these are going to be big comments that we haven't gone like crazy into, but I'm confident you've seen. We use SOHCAHTOA. And we probably have something similar to this yesterday, but I just want to stress it here. We use SOHCAHTOA to find a side length if we are given an angle. Okay, so if I tell you an angle, you can use SOHCAHTOA, but it turns out if you can use SOHCAHTOA, there's pretty commonly going to be a situation where you've been given 2 sides of the triangle anyway, and Pythagorean theorem would also work. Now, sine, cosine, and tangent, remember, they're all functions, and we don't necessarily always see them like that. Did you guys graph the waves and stuff last year with sines and cosines? Did you graph a wave ever? So just to check, maybe it seems familiar because it sounds crazy. If we graph y equals sine theta, you ever graph things like this that look like this big long wave? Cool. Probably in Algebra 2, at least basic idea. We'll do a lot of it in here, pre-calc anyway. Cool. Other piece. There's another option, though. Maybe we don't want to find a side length. Like, side lengths matter. That's our magnitude of any vector that we deal with. But what else might we wonder about? Every vector has 2 things. It has a magnitude and a direction. What if we want to find the angle instead of a side length? All right, so check it out. We're going to make a little comment, and apparently check it out has become like my new catchphrase. And I was about to start writing it just there. Weird. To find the angle theta from side lengths. We use, and then we're going to do a little bit of scratch work off to the side, which don't mind if you don't write it down, but I need you guys like attention and stuff. And again, speak up if I'm going like super duper slow or super duper fast. So here we are. I'm just going to make up a little claim here. I'm going to say that I know for a fact, well, I don't know for a fact, but we'll say it. The sine of an angle theta, let's say, is equal to A over B. It's some ratio. Okay, this happens every single time. If I wanted to solve for theta, how do you undo a sine? Like, really common that people want to do this. Don't write this. Is this allowed? Because we're not multiplying, right? This isn't a multiplication. This is the sine of an angle theta. It's a function, just like f of x. You can't just divide by f. Well, gosh. How do you undo addition? You use its inverse. Subtraction. How do you undo multiplication? You use its inverse. Division. How do you undo trig? You use its inverse. So we're going to make a comment. We use inverse trig. That's what this is going to wind up at. And I'll write that here in a second. But the way that I write this is probably a little bit different. You guys have seen it guaranteed. Sine with a -1 exponent to show the inverse. Okay. As long as I do the same thing to the left and the right, am I allowed to do it? Okay. I'm going to show this one time. We'll see it again in pre-calc. When I take an inverse, I always use capital S to make sure that it's like really clear that this is different. The -1 exponent is a terrible choice of notation, but I didn't pick it. I didn't write the rules or something along those lines. Check it out. The arc sine, or the inverse sine of the sine of theta. If I took the inverse sine on the left, where else did I have to do it? On the right. At this point, have I done anything that looks like cheating to you? Everything you know about algebra feels okay here? Okay. What happens when you take the arc sine or the inverse sine of a sine, or the inverse of its inverse? That's a weird way to word it. This is one situation where I'm okay with this word. What do these do? They cancel. They undo each other because that's what inverses do. We would be left with theta is equal to the arc sine of a over b. We have successfully just solved for theta. 30 years ago, we would have big books in here that volumes of them that are this thick that have angles listed, and you'd have a volume of 0 to 10 and so forth, and we have to go and look them up in a book. We don't have to do that anymore. What do we get to do when we're trying to find these angles? CAL. See you later. Cool. Your calculators do it all. We're not going to look anything up. Cool. All right. We use inverse. So katoa. Now, you may have noticed, and I don't care which one you use, I don't know that I'm going to be able to change it because I'm pretty set in my ways with this one. If I said read this, just that sin to the -1, how did you guys learn to say it or read it? Or what do you say in your head? Pronounce that. Did you guys use inverse sine? Okay, inverse sine is completely acceptable. I prefer arc sine. ARC, it's literally, you can either say one of these two words just as we're talking about it, and I can try to be consistent. Inverse sine is one option, or arc sine. I like to write the inverse one. You could write this instead of the exponent. I prefer to say arc sine. Any objections? What do you think undoes a cosine? So we're going to try that again. What do you think undoes a cosine? Arc cosine. So you guys committed to arc. Okay, cool. What undoes a tangent? An arc tangent. Sweet. Okay. We need a couple more trig rules, but just to look, should we do a problem just with the things that we have now? Let's do an example, and then we'll expand our trig knowledge just a skosh. I don't have a worksheet because I knew we were going to just be doing this today. Do you want a math trig problem or a physics trig problem? Math? Okay. You know what? They're actually going to be about the same in here. So, example, you walk 3 kilometers north, then turn. Are we turning east or west? West, sure. And walk how much further? 113 sounds good. Okay, assuming, and I'm not going to write up the whole context, but let's just say you're at a camp and you've now left, or I don't care where you are. But straight north and then straight west, that far. I want to know displacement. Find two things, total displacement and its direction. All right. So I offered you guys math or physics, and then it just turned into pure physics, but that's okay because this is how the math is also approached. Okay, should we draw it? Probably. Looking at it, I'm just going to pick different colors. Here's my starting point. Is it going to be perfectly to scale? No, and actually it's going to be terrible to scale because I picked an obnoxiously large number. Cool. Here we go. I just walked this direction. How far is this? 3 kilometers. Love it. That's part 1 of my trip. I then start here and I go 113, which again, not to scale, to the west. 113. And I'm going to change colors so we can talk about them separately. 113. And then my total displacement is this guy. Now, there's a couple interesting things that are going to happen with this. I'm going to call this R for now, capital R, for my resultant, because I'm just adding 2 vectors. Could we use Pythagorean theorem? We could. Are we going to? Not a chance. Okay, I am confident, at least mostly confident, that you guys are all like fine with the Pythagorean theorem. I don't really have an issue if you use it on your stuff, but I want to get trig practice. What angle is this? 90 degrees. I agree. Okay. For this, we are going to find the length of the resultant using trig instead. We're not going to use Pythagorean theorem. We can verify it if you guys want. But let's take a look. It doesn't really matter which angle we go from, but maybe we need the angle first. If I said, what direction are they traveling? Can you guys estimate for me if this is due north? Estimate the direction they need to travel. I'm going to give you a second because you're going to be looking for an angle somewhere. If you want, I'll make it really faint. It's really not that faint, but that's a horizontal, right? What would you estimate this angle at? $60, maybe? Like, I can see that. You're talking this angle, I assume. Like, maybe that's the angle you're talking about, or were you talking about this side? Okay. So I agree this is probably pretty close to 60 or 70 degrees. Anybody come up with a really low number because you were looking at this? Anybody come up with an obnoxious number like, well, I don't know, 150-ish? Can you see why I could come up with 150? Okay, because it's 90 plus that, right? All right, so here we go. If we're looking for the angle, we talked about bearings a little bit yesterday. We always start at north or south. Is this angle, if we're looking at the direction of actual travel, closer to north or closer to south? So that's a weird way to word it, but here's what I mean. You agree that's how far I have to turn to get to north? And to get to south, I have to turn this far? Am I closer to north or am I closer to south? I'm way closer to north. So my bearing is going to be north and then some amount of degrees to the west. That's what I see happening here. Cool. I'm going to label this theta. We are first going to find theta. Right off the bat, we're going to find theta. Now, from this angle theta, and it depends on which angle you go from, so it's like subjective. I know that I have two sides from this angle theta. I have this side, and I have this side, right? Now, in all of SOHCAHTOA, there's only three sides we ever reference. Opposite of an angle, adjacent to an angle, and the hypotenuse. This side on this particular problem, right up here, the 113, is that opposite, adjacent, or hypotenuse? From this angle theta. Opposite. Okay, this is always the hardest thing, but I think that we'll be okay here. The other side length of 3, Huggins at 3 kilometers, opposite, adjacent, or hypotenuse from that angle that we have marked.
The 3?
Yeah. Adjacent, perfect. How'd you know it wasn't a hypotenuse? Yeah, hypotenuse is always opposite from the 90 degrees. Cool. Run through your famous Lakota chief, and that is not going to make as much sense in here because we didn't do the big long story. Which trig function has opposite and adjacent? So check it out. If I wanted to, I know that the tangent of which angle are we looking from? Theta. Tangent of theta is equal to, what's the opposite length? 113 over, what's the adjacent length? 3. Now, does anybody know off the top of your head what angle theta makes this happen? Me neither, not a clue. Not like I have a guess only because I've drawn this kind of to scale. Man, if we wanted to solve for theta, how would we do it? How do you undo a tangent? You take the arctan. Now, normally, if I take the arctangent to the left, do you agree tangent just falls out? I'm not even going to write that I've done it over there then. That angle theta is the arctangent of 113 over 3. Do me a favor, grab your calculators out of your desk, and just a heads up, we're going to be switching back and forth over and over and over between this class when we do trig and we do trig in pre-calc. First thing I need you all to do, did I borrow somebody a calculator yesterday during the test in pre-calc? Did I get it back? Where did you, were you sitting right there yesterday for the test?
Yeah, but I put that calculator back in the front.
Okay, I'll find it. Okay, right off the bat. You use mine. Were you? Okay.
Because I remember you giving me one. It's just.
Will you do me a favor? Is that HK high? Or we can slide it down. Okay, so I'll steal that one back at the end. I'm going to order just a classroom set of not as fancy calculators. But cool. Do me a favor on the very top. I'm going to talk to people next to you for a second. There's a button that says mode on the top. Do y'all see it? Turn your calculator on and hit the mode button. Did you see the message I left on that calculator yesterday?
No.
Did it say nerd when you turned it on? Oh man, bummer. All right. All of a sudden you get a lot of options, right? We're in normal mode, I assume. Our float is just set to float. The third one from the top, there's one of two things highlighted on this calculator. Is it highlighted right now as radian or degree?
Degree.
Change it to degree if it's not degree. If it's in radian, change it to degree. If it's in degree, keep it degree. Cool. Once you're there and you've highlighted successfully degree, go back to your home screen by hitting second quit. Where's the arctan button?
The
Second tangent, and tangent is either above 7 or 9. I don't remember which one. Ask your calculator the arctangent of 113 over 3. 88? Point what? Okay. 88.47 what? So okay, so I'll call that 4.8 because I'm around it. But 88.48 what? How do we measure angles? Degrees. Cool. All of a sudden, we now know that this angle is 88.43 degrees. So we're getting our answer in a weird thing here. I know my angle. That's just this angle, though. That's north, and then turn 88 degrees to the west. Good. You could call it south, but I'd be wary because check it out. If I'm at north, I can fall this way to get to south, or I can fall this way to get to south. It just doesn't give me enough of an answer. Cool. We now know that that is there, but we're also we found the direction. Cool. What about its displacement? How do you find the length of this without Pythagorean theorem? Do we know an angle now? Oh man, do we know at least one side? Cool. I don't care which side we use. We should probably use 3 because it's easier. If I go with 3, and I guess easier is subjective because your calculator's doing it. I don't really care how easy it is. Well, gosh, is there a trig function that relates from angle theta, the adjacent and the hypotenuse, or if you'd rather, the opposite side and the hypotenuse? Are there trig functions that do that? Which one relates adjacent side and hypotenuse? Ca, or cosine, and opposite side and hypotenuse? Sine. So, yeah, okay. Turns out you can use either because we have enough information. What feels more natural, or what do you like more, sine or cosine? Cool. So check it out. We're going to do the sine of this angle, which we just found it. And I'm going to continue over here. The sine of, what was that angle? 0.48 degrees equals, what's the opposite side length from this angle of 88 degrees? 113 over, what's the hypotenuse's side length? R. Cool. We don't know it yet. Check it out, though. We have a single equation, and there's only one unknown in everything. I would rearrange it before I plug stuff in, but I can probably do two things at once. If I want to solve for R, I need it out of the denominator. How do I do that? Multiply by R. So we would get R times the sine of 88.48 equals 113. And then this is a hard thing to get over, but we're going to start seeing it more and more in both classes. This thing is a number. It's just a number. It's an ugly number right now. It gets uglier if you type it in because you're going to get a big, long, irrational decimal. Sine of an angle is a what? Sorry, let's try to see. Sine of an angle is a what?
Number.
Just a number, which means cosine of an angle is just a, and the tangent of an angle is just a number. Because it's just a number, if I have R times a number and I want to solve for R, how do you undo a multiply by some number? You divide by that number, right? This number happens to be ugly. On your calculator is where I would answer this. It's 113 divided by, what was that number that we're going to divide both sides by? The sine of 88.48 degrees. And we'll see if it makes sense, because it maybe looks like it doesn't to you, but we'll see that like it will. Probably pretty close to this number. What is it? So the magnitude of R is 113 point what? 04. Okay. Now, does this feel like a good or a bad answer to you? Does this logically make sense to why it would be this? If it doesn't for somebody, you do not have to do this, but I'm going to try to draw it a little bit more to scale. Here's 3. Here's 113. Is this length pretty close to the same as the other one? Reasonable. Like, I can see that when we draw it to scale, that really does make sense. We're going to knock out our answer real quick. So here we go. What was the actual question? Find total displacement. There was no real context and stuff. I'm just going to say, what is our displacement delta x? 113.04 kilometers. At angle theta was, and we have to be really careful here, we cannot just say 88 degrees. Because if I said, hey, you guys stand up and walk at 88 degrees, you're going to walk this direction. Because normally you're going to measure from the positive x-axis. That's a natural choice. How did we say we're going to discuss this bearing? Do we start at north or south? We start at north. Then we turn how far? So 88.48 degrees. And we turn which direction? Boom. There's our bearing and our displacement. Sweet. Okay, this was about as fast as I can do trig with not just saying, here's a formula to use. Do you feel better right now with trig than you did an hour ago? Okay, tomorrow we're going to see what happens if it's not a right triangle. Thank you so much for coming in today. Please remember that on parties of 10 or more, gratuity is typically automatically included. But if you feel like the service was exceptionally great today, you can always leave extra with our wait staff. Later, Raiders!